Hello, everyone. Thank you so much for joining us for our new Young webinar. So without further ado, we are going to start. But first, let me present as I have already as you already know by now, we are going to start with the introduction of our Young Society, which is Young ESPGHAN. So today we are going to talk about the role of machine learning and AI in pediatric GI, and we are going to have our speaker, Dr. Sana Syed, but I will going to introduce her a bit later. So as you know, our committee mission is to promote high quality research through and training and to organize activities for our young members. But most important, our aim is to represent the interest of our members within the council and our society. Regarding our Young ESPGHAN educational event, we have the mentorship program, and this year is our third edition, and it's a forum for ESPGHAN training members to meet and receive support from more senior members of our society. And we have already the deadline for this mentorship program has already it was in the past. I'm so sorry. But now we are going to have the interaction between our training members and their senior members during our conference now in Helsinki. Regarding our Young ESPGHAN Day, this was held last year at the National International Congress, and we are going to talk about a new Young ESPGHAN Day that is getting really close. Next month in Helsinki, and we are going to have multiple surprises for you, so please join us. Also, during the Congress, we have Meet the President, where you can ask the president of our society all the questions you would like to receive some answer regarding the involvement in the society. So this is our team, our Young ESPGHAN committee. We have Anne-Marie, that is our chair, but also Vangelis, that is our Young ESPGHAN secretary. We have Petra, that is our treasurer. Anna, that unfortunately is no longer one of our members. Pinar, and we have Francesca, that is our social media ambassador. Myself, we have Jose, Giovanna, Harwin, and Beno. So if you're not a member yet, please join us. You have multiple benefits as a training member. You have the subscription to our GPGN journal. You can have access to different awards. You have access to different courses, and you have the access to Young ESPGHAN networks and the possibility to take part to our educational events. So how to become a member? You need to fill in an application form that you can find on our website, but also you need your CV and a letter of support from a full member that is not serving in the council. Also, you can follow us on the ESPGHAN app, and also you can follow us on Instagram. So again, if you're not longer a member, if you're not yet a member, please join us. Also, there are different educational events as different courses that you can take part of. For example, the next courses is the Eastern European Summer School, the Hepatology Summer School that is actually going to be held in Romania, that is my home country. And also you can have the colonoscopy trainer study day. So you have multiple courses and you can take part in different ones. We are already at the end of April, so we are going to see each other hopefully in Helsinki next month. And as a Young ESPGHAN committee, we have prepared for you multiple surprises. For example, during the Young ESPGHAN afternoon, we have an workshop that we are going to find out more about decoding research, systematic reviews, meta-analysis, and peer review essentials. So you are going to gain insights into statistics and meta-analysis under the guidance of the renowned Professor Maurice Gordon. And you are going to gain a basic understanding of statistics, learn the fundamentals of systematic reviews and meta-analysis techniques, and you are going to identify the importance of peer review in your daily practice and career progression. Also, we are going to have during the Saturday session a Young ESPGHAN event, navigating clinical cases for young professionals. So if you ever had any sleepless nights thinking about a patient's case, or if you have encountered clinical scenarios that haven't really gone the way you hoped, we have prepared this perfect opportunity to ask the experts in the field of pediatric gastroenterology, hepatology, and nutrition. We have already chosen a few cases from the ones that you submitted, and hopefully we are going to have a great interaction and we are going to find out more interesting things about these difficult cases. So we are waiting for you during our Saturday session to join us. Regarding our webinars, we are not going to have in May one because we are hopefully all going to see each other in Helsinki, but starting with June, we are going to talk about the gut-brain interaction, and then we are going to talk about life-saving nutrition, and in August, we are going to talk about the nutritional management of eosinophilic GI disorders. So please join us for our upcoming webinars. Without further ado, we are going to talk today about the role of machine learning and AI in pediatric GI. So I'm going to introduce our speaker today. That is Dr. Sana Syed. That is an associate professor, a clinical investigator, and a pediatric gastroenterologist at the Duke Clinical Research Institute. And over the last decade, Dr. Syed has gained international recognition for her expertise in translational data science-driven research to advance our understanding of undernutrition in the context of intestinal inflammation in maternal and child health. And this cutting-edge work has been supported through her impressive track record as principal investigator and on numerous federal and foundation grants, and also awards from the Gates Foundation and Zuckerberg Initiative. Dr. Syed's research employs cutting-edge omics and computational methods such as artificial intelligence and machine learning-based techniques to characterize the metabolic shifts, genetic signatures, and tissue features associated with subtypes of pediatric inflammatory bowel disease. It is at this intersection of data science and precision medicine that Dr. Syed continually seeks to further medical diagnostics and treatment paradigms to improve outcomes for all. So please join me in welcoming Dr. Sana Syed. Thank you so much for accepting our invitation today.
Well, thank you, Mara. I'm going to go ahead and share my screen. So can you guys all see that? And
yes.
If I'm forward.
It's perfect.
Okay, perfect. So thank you for that wonderful introduction, Mara, and for the opportunity to be here. I know some of you guys had seen me speak at the World Congress, and I actually was in Milan and for ESPGHAN last year. I'm not planning to come this year, but I just loved the conference, and it was very good. I'll tell you one of the best things about it that I liked was that there was like a mother's nursing room, and it was all this support that we usually don't see on this side of the Atlantic. So I'm very excited to be here and help answer and teach in whichever way. So I don't have any current or past relationships with any commercial entities. And so this slide is really just to show, when I was looking up artificial intelligence, just to do a lit search before any talk, I was looking to see what do we have as resources, maybe in peds, not so much in PGI, but in pediatrics as a whole. And I don't know of equivalent organizations in Europe, but AAP is where we get our board certifications, extra form, American Board of Pediatrics. And as you can see, there's a wealth of webinar series there. So I would encourage anyone who's interested, because my talk's going to be really a broad overview. So I encourage you all to explore these offerings. So now that we've kind of seen an example, a summary of what all is available out there, this is the outline for my talk. And I'm going to start off with talking about AI and ML today and how we go about it. So I know it's a webinar, but can everyone take out their smartphones? I'm going to give you a second, right? And I want you to log into your smartphone. I'll give you another couple of seconds. And done? Yeah, great. So the reason why I asked you to do that is AI and ML are already here in our world today. I'm going to talk about artificial intelligence as AI and machine learning as ML moving forward. And so what just happened in your hand was your phone had a large training data set on which a machine learning algorithm, most likely a convolutional neural net or deep learning, had developed a unique algorithm that fit your face. And when you put your face, now you were the test set. And clearly the algorithm is really good because it opened your phone. I'll tell you something funny. When I log into my smartphone, if I'm very happy or very sad, it doesn't recognize me. So I have to have very neutral. So my algorithm still needs tweaking. So the point I wanted to tell you is that technology is all around here, everywhere. And the way we know how to implement and think through logistic regression in our research and our clinical work, we should be able to use AI and ML in that same sort of facile way. And so I thought we could spend the next 3 slides talking about some big concepts so you can see what this technology can do and what it's capable of. So just starting on the top left, the biggest idea to understand is that that AI ML allows you to understand the underlying function. So the function of my face, or that describes pattern. And we see a lot of words, so AI, ML, deep learning thrown around. And this is just to give sort of an overview. So artificial intelligence is the broadest concept. That's sort of your Tesla and auto drive. So you're driving, you put the address in, the Tesla decides where to turn. You're not doing anything. You're there to override if you need to. But the AI algorithm is making an independent decision based off its previous input. I don't think we ever want medicine to be there, but I think we always want a human in the loop. So then the second part is machine learning. And machine learning, I'll talk a little bit more about that. That's more broader, again, all sorts of data, different kinds of algorithms. And deep learning refers to a very specific type of algorithms called convolutional neural nets. And they really have the ability to pick up features across images. And I always like to put women, and so that's a picture of Ada Lovelace. She was a British programmer in the 1800s, and she was one of the first to recognize that computers had a much larger potential than just computing math. And so the next thing I want to show you is this idea of what we know versus kind of what ML is. So when you look at traditional stats or programming, we're used to having, so here's our data. If it's normally distributed, if it meets XYZ rules, then great, I can use linear regression or logistic regression, and I can answer a question. We have a bunch of X1, X2, X3, say you're predicting anemia. So that can be a logistic outcome. So you use logistic regression. And so that's your typical traditional stats. There's a lot of challenges to that. The rules, so the algorithm may not work as well if your data is not perfectly normalized. And then that's sort of the same concept with classical programming. Now, machine learning is when you have the data and the answers, and then the machine figures out the rules, right? And so the most intuitive way to think of that is, like I said, that straight line example. And so what's interesting is if you take a data set that is a straight line data set, and even if you use deep learning on it, the underlying algorithm it'll find will be a straight line algorithm. So the often, the question I get was, oh, let's just use AI on this. And the biggest thing I'll say was, well, you don't need to use AI for everything. Because it'll essentially come down to the simplest algorithm. And so if you can just use the linear regression, then go ahead and use it. But often in these complex questions that we're looking at these days, such as, what is the function representing Crohn's disease in a stained H&E biopsy? That is something a machine learning algorithm would be able to figure out. Now, if the function may be this wiggly pattern in like multiple dimensions, that's fine. It's hard for us to visualize that, but our machine learning algorithms would allow us to do that. And so one other way to just help understand intuitively, and I'm spending this much time because I found when I started doing this work, I had this fear of some magic happening, right? And so I think like when you can just see in a very intuitive way what the algorithms are doing, then you feel more like trusting it. So I've given image analysis as an example because that's a lot of the work I do. So usually you think of numbers in 2 dimensions, so Excel rows and columns. Machine learning depends on matrices, which can be multidimensional. This is a 3-dimensional matrix I'm showing you in which the color RGB, which is what we use for our digital images, that's a 3D matrix. And then the combination of those numbers and values is how the computer sees the image. So each RGB channel has a pixel associated with the color. And that information is what those numbers are what the algorithm reads and comes up with the underlying function. Now, what's interesting is that even though there's this big push, and over the last decade or so, we've been hearing about deep learning, et cetera, a lot, the algorithms that were developed that are being used now are actually developed way back in the 1960s and 70s. I wanted to point out 3 people. They're called the godfathers of AI or deep learning. So starting from the left, Yoshua Bengio, he's a Canadian-French scientist currently in the University of Montreal. Jeff Hinton, who's at University of Toronto, and Jan LeCun, who's a French scientist currently working at Meta. All of them in 2018 got the Turing Award, which is considered the Nobel of physics. But then Jeffrey Hinton didn't go on to get the Nobel Prize for physics last year. And then Phoebe Lee, I always talk about, she's one of the biggest forces that led to labeling data sets. And so, in the early 2000s, they're like, okay, great, we have these algorithms, and people were just trying to write the perfect algorithm. And she said, well, all the data is digital now. What if we just label it? And then once you have all these labels, then the algorithms can train off them. And she got a lot of critique. And I mentioned that to say it's important to stick through with your idea and know when you shouldn't give up, because every algorithm related to convolutional neural nets is trained off ImageNet. It's actually embedded in any Python, you name it, TensorFlow notebook that comes out. And then the last person I wanted to bring out to you is, and her work is what then led and brought us to things like ChatGPT today. So the last person is Eric Topol, who's at the bottom of the slide. And he talks about how there are these industrial revolutions, and the world is currently in the 4th industrial revolution, and medicine is still stuck in the 3rd. And we sort of all intuitively know that. So we have EHRs, we have digital radiology, but we're not quite as facile with it, in which we are being able to use it to the max way possible, the way your phone. So your phone is clearly in the 4th industrial age. And I think a part of that is getting physicians like you and I to understand big data and then use it in ways that would help our patients. And so in gastroenterology, we acquire data from a number of different sources. So I'm going to give a few examples each of language models, radiology, endoscopy, pathology, and then talk a little bit about our multi-omic work. And so just starting off with language. So there are 5 areas that this is a paper in which LLMs were looked at to see what are the big areas of applications. And what they looked at and showed was you can use it for research, scientific writing, education to keep health personnel up to date, clinical guidance for physicians, and answering patient questions. And I'm going to follow this slide with 2 examples. One's actually by PGI fellows at Duke. And then actually it ended up being another example from Duke of, again, using large language models in those specific areas. I think the big point is, so on the right, you can see a bunch of different kinds of LLMs that are labeled. Lots of us will have heard of ChatGPT. There's obviously Gemini, et cetera, that's come out now. The point here to say is that these LLMs need to be refined and adapted to specific medical contexts and guidelines. And I'll give you a few examples of how this has been done. So this is a poster. These are 3 GI fellows at Duke, where I just started work in January. And their work is going to be presented as a poster in DDW in May. And so their goal was to assess the performance of Microsoft Copilot, OpenAI, ChatGPT 3.5 and 4.0 on the 2022 and 2024 AP Prep GI assessment questions. And so what they did was, when they did use these 3, what they found was that all 3 passed Prep GI assessments. OpenAI GPT 3.5 passed 2003 and 2004 Prep GI, but it didn't pass the 2023 assessment, so it got 60% in that. There was no big difference between the different chatbots over the 3 assessment years. And one of the interesting things we found was, so, obviously these were chats, words that had been copied and pasted, so they were unable to put the media. But the 3 chatbots were able to answer 50% or more of the media files, which is just interesting, I think, from a trainee perspective, to like tell folks that the text has a lot of information, even if you don't understand the image. The other thing I really found interesting was that the chatbots collectively scored best in anatomy, allergy, dermatology, motility, research, mouth and esophageal disorders, but they didn't do well in physiology, pharmacology, liver disorders, stomach, and duodenal disorders. And that just kind of tells you, there is, obviously training that they're happening as they're taking these, but it's what's out there in the world that's probably not as well representative of these areas. So it's in their large conclusion was that that these newer advanced AI chatbots pass the Prep GI assessments. It shows that these have potentials as teachers or as ways of helping facilitate a patient training, fellow training. And here's a QR code in case anyone is interested in looking at the presentation itself. So this is another example. It's a study by 2 adult gastroenterologists, Jacqueline Henson and David Lehman. They studied ChatGPT as a clinical tool. So they did it in the context of GERD, as you know, affects nearly 30% of adults in the US, and managing GERD is becoming more and more complex. And so they asked, could ChatGPT serve as an interactive resource tool for patients experiencing GERD symptoms and a support tool for clinicians, so both for patients and clinicians. So they developed 23 prompts across 3 categories, and they based this on decision points from published clinical guidelines and expert consensus guidelines. And then they gave each prompt to ChatGPT 3 times, and then they had the responses rated by 3 board-certified gastroenterologists for appropriateness and specificity. And then 8 patients reviewed the representative response to the prompts as well. And they assessed whether they could understand the information, whether they found it useful for medical purposes. And they kind of just compared that to sort of Google, which they would have done otherwise. And the team found that ChatGPT delivered appropriate responses 91% of the time, and most responses, so 78%, contained specific guidance. And patients found it 100% universally useful, which I think was really interesting. But the point for us is always the false positive. So about 9% of responses were either inappropriate or inconsistent. And so the take home is really the same as the previous one, which is their effectiveness in real world medical practice depends on thoughtful integration. And the goal is that they enhance and not just replicate physician capabilities. And I think that's kind of the point about Tesla. The goal, I think, of AI and all the work we've done is not to say we're going to replace a pathologist or a gastroenterologist. It's to help augment. And so I'm going to move on to the second type of big data we use in GI, which is radiology. And you'll see I'm giving you peds examples where it's possible, but we actually don't have a lot of pediatric data. So just bear with me. And I think a lot of these do apply to peds. And so hopefully this will inspire some of you to do a similar project, but in pediatrics. So this is a study conducted by Dr. Bihong Chen and her team in Shenzhen Women's and Children's Hospital in China. It was focused on Crohn's disease. So while CT enterography is commonly used for diagnosis, its imaging findings often overlap with other bowel conditions, and that can make diagnosis challenging. So the study explored radiomics-based ML to detect bowel lesions in Crohn's. This was a retrospective study of 139 adult patients. They extracted features from their arterial and venous phase CT enterography images, and they compared Crohn's disease to normal bowel segments. And what the results showed that the classification model demonstrated a high performance and high accuracy, had an area under the curve of about 94, so, and an accuracy also of 94 for arterial phases. And then the venous phase images had an AUC of 96. So what does this all mean? The classification model basically demonstrated a way to distinguish Crohn's lesions versus normal bowel using radiomics and machine learning. And this would be something, applicable maybe at a community center, or where you don't have a radiologist who are experts in IBD, or maybe where you don't have a radiologist and needs sort of a screen done to decide whether someone needs to get referred to a tertiary care hospital or not. This is a pediatric studies from Cincinnati Children's from Jonathan Dillman's group. Now, their goal was to develop a deep learning model which uses clinical data and anatomical MR imaging data, so non-elastography data, to predict which patients would have normal liver stiffness. Therefore, they would be able to target and decrease the use of MR elastography, which would then help, reducing imaging time, healthcare costs, etc. So they made a convolutional neural network, which is deep learning, and they call the model Deep Liver Net to categorically classify liver stiffness in pediatric patients with known or suspected chronic liver disease. So their goal was no or mild liver stiffening or moderate to severe liver stiffening. They did axial MRIs, clinical data, and MR elastography stiffness measurements. And when they did their internal cross validation, they did it with 178 patients. And so what they found was that the combination of clinical and imaging data produced the best performance, area under the curve of 86, compared to clinical only, which was 83, imaging only, which was 80. And the DeepNet correctly classified patients with an accuracy of 88, sensitivity of 74, and specificity of 95. And then when they did an external validation, they saw similar results. So this study shows the potential of risk stratifying liver stiffness and directing the use of MR. So again, the idea is not to replace a pathologist, radiologist. The idea is to say, in which instances do we need to do this longer study? And as you know, kids need to be sedated, et cetera, et cetera. Can we take regular images and lab data, use that to figure out which kids need that additional longer imaging? And so I'm going to move on to endoscopy. Now, endoscopy is actually where there is probably the least amount of pediatric data. I wanted to show you sort of two position papers. The one on the left is by Adult GI. It's a white paper focusing on 3 areas, and they've talked about priority cases for using and developing AI algorithms in GI. So for specific clinical scenarios, for streamlining clinical workflows, for quality reporting, practice management. The second area they've done is data science priorities for big image libraries. So that's the biggest gap. Like the reason why, we actually started a project on small bowel endoscopy video capsule AI, but it was just so painful trying to get enough data in pediatrics. I think I agree with that gap even for pediatrics. In adults, it's a gap that they've talked about. And then how to standardize, store, share, annotate videos. And then in research priorities, they really talked about high quality prospective trials. Now, the only thing in pediatric GI that's published, even in terms of sort of a broad view, is by this group at Cincinnati Children's. And they've sort of talked about the summary of peds endoscopy and current status, future applications. So I encourage you to go read those papers. I just thought it would be a good context sort of set. Now, this was actually really interesting. This is pediatric GI. So this is a study that aimed to evaluate the use of AI-assisted virtual reality on pre-op anxiety levels and vital signs in children undergoing endoscopy. So not maybe exact GI, but an application of GI I thought would be interesting to show. So this was a randomized controlled trial design, had a total of 80 children, 8 to 17, half intervention control. In the intervention group, they got VR applications, so space and underwater themes, and the control group got standard procedures. And then they had different anxiety assessment tools. And what they showed was the VR applications had significantly reduced anxiety scores. And same thing when they used vital signs. And so their broader conclusion was that this is an effective non-pharmacological method for reducing perioperative anxiety and promoting physiologic stability in children. And so this holds the potential to enhance their experiences during invasive procedures. So again, a way of enhancing but not replacing what we're doing with our patients. So the next example, this was I was going to share. We had done work like this before. It's interesting now. There's actually a company for it now. So on the right, you can see FDA and the pill. So this is actually a commercially available tool now called NaviCam. And what I've done is I've shown you the paper and the research that led to that. So the paper was the research project that's published here. Their goal was to develop a deep learning-based algorithm, so a CNN-based algorithm, to assist in the evaluation of small bowel capsule endoscopy. Now, they had a very, very large data set. So they had 113 million images from almost 7,000 patients from 77 medical centers from 2016 to 2018. And they used this to differentiate normal from abnormal. And the images were categorized as normal, inflammation, ulcer, polyps, so on and so forth. And then they validated it in 5,000 patients. So you understand how large this study was. And so those patients were evaluated by conventional analyses. And then the CNN analyses was evaluated by 20 gastroenterologists. And so where there was agreement between conventional and the deep learning model, there was no further evaluation. If there was a disagreement, the gastroenterologist reevaluated the image to confirm or reject the CNN classification. So what they found was that the CNN model identified abnormality is 99.88 sensitivity per patient analysis, and the 99.9 sensitivity in per lesion analysis. And so conventional gastroenterologist leads actually had abnormalities with about 75% sensitivity and 76 in the per lesion. Now, what was really remarkable was the time, and you can imagine how much faster the algorithms take. The mean reading time per patient was 96 plus minus 22 minutes. So 96, over a couple of hours by conventional read. And it was 6 minutes plus minus 2 by the CNN system. And so I think, the biggest value of this was it is higher sensitivity, higher specificity, and a lot shorter reading time. And again, the tool would allow you to look at things that is incorrectly classifying, and it would show you its results. I remember going in and spending hours in fellowship doing these capsule reads. It was actually one of the reasons why we started that project. And I'm really excited to see this as a tool on the market now. So moving on to the fourth type of big data, which is histology. And I'm looking to see we're okay on time. So the first example I wanted to show you was of Hirschsprung's disease. So this is a group based in Germany by Dr. Uday Rolle. The aim was to see if AI/ML methods could distinguish between healthy versus individuals with classical Hirschsprung's using digitized slides. And so often it's the case that Hirschsprung's disease is diagnosed from rectal biopsies, which have cholinergic hyperinnervation and aganglionosis. But with different methods of acquiring the rectal biopsy, the diagnostic accuracy can vary substantially. So this was a retrospective study. They had 112 samples, pediatric samples, with 112 patients with 283 samples. And the scopes were over a period of 10 years. So they had slides that had ACHE staining, and those were rectal samples. They were digitized and then analyzed with the digital imaging software. So the point here to make also is this is a tool that already exists as Halo and QPath. So they use software that's already on the market. So they applied the ML algorithms to detect patterns of cholinergic hyperinnervation. And the AI analysis showed high precision into identifying disease with an area under the curve of 96. And so their larger conclusion was that these findings suggest that software-assisted ML analysis can enhance the diagnostic accuracy of disease. And so over the last 10 years, one of the things that I found really useful is these were algorithms that we were having PhD students and data scientists write. And now those algorithms are out in the market the way, your phone has these algorithms running in it. I think that's really fascinating. I think the big piece that'll move us forward is just this ability to get more data out there. My personal passion is trying to get more and more histology data out there. because that's actually one of the hardest to get out in the open space. And I'm happy to talk about sort of what sorts of efforts we've been making. So in the next couple of slides, I'm going to talk about work our group is doing as an example of digital histopathology and precision IBD medicine. And so, as you all know, well, not so in Europe, but in the US, the only FDA-approved biologics are anti-TNFs. But about 20 to 30% of patients do not respond to biologics. And I have a picture of James Woody, whose group led the first work showing treatment of Crohn's disease with anti-TNF agents. So our question was, can we predict patients who will respond to anti-TNF biologic therapy or not? And so this was a project where we set out to build a model, so a custom model to identify tissue features that predict a response to anti-TNF therapy or not. We had initial support from the Crohn's and Colitis Foundation, and then went on to have sort of more institutional funds, et cetera. This was across the University of Virginia and Innova in Washington, D.C. And this was, as with most IBD studies, our cohort was relatively small, so we had 52 subjects. Our aim was to use tissue features identified by the model to predict TNF response versus not. And so in this slide, you can see that our computational model was able to accurately classify a patient as responding to therapy at 100%. It was also able to classify non-responders with a lesser degree of accuracy. And this is really about the power of data. So we had lots and lots of responders, but not as many non-responders. So obviously the model had less to train off. And then beyond just being able to classify an image as being responsive to therapy or not, we were also able to use saliency maps. So the whole point is being able to visualize the black box. So, way early on in the presentation, I talked about, well, if you can use a linear regression, use a linear regression. Because a linear regression will give you betas, it'll give you these measures of what the model is weighing amongst different variables. Deep learning models typically don't give you those kinds of weights. But in image analysis, there's been really great advances that have led to things like these saliency maps. So saliency maps are basically heat maps. And so here you see the highest activation is in the purple and blue, and the lowest activation area is red. And then what we do is we have these saliency maps read by our clinical pathologists. So we have 2 GI trained pathologists, Chris Moskalik and Shyam Raghavan, who've been working with us now for many years. And then when they reviewed these, they determined that the areas that were highlighted as significant between TNF response versus not were a lot of lymphocytosis and lamina propria and the epithelium of the tissue. And now, the question would be where and what would be the biologic relevance of the tools being established by the model. There was another model we used, which was just a specific cell detection model. So the cell segmentation approach looked at connective tissue density, lymphocytes, plasma cells, and other cell types. And as you can see, there's a significant difference across all except for eosinophil density. And so the work from this small scale study actually then led to an NIH study, which to date, we have been told is still funded. As you can imagine, with all the federal changes happening in the US, we're still funded, don't know about tomorrow. But this is a project between Duke, UVA, and Emory. We're establishing a much larger database to the tune of at least 500 or 600 patients. And the study will generate a machine learning model capable of predicting future IBD outcomes. And our goal is to add more multimodal data, so lab markers, radiology, et cetera, not just the histology. And then we're also going to do state-of-the-art spatial and single-cell transcriptomics with the goal to allow us to do further characterization of the regions that are responsible. So, we could potentially go and look in doing spatial transcriptomics, look at those areas on the slides and do spatial omics to see if there's a different functional genomic profile in the areas that are being highlighted by the model. And finally, this brings us to the last type of medical big data, multi-omics. Some of you may know, part of my interest is also in global health. So we study inflammation in the context of nutrition. In the global health, it's in a disease called environmental enteric dysfunction. In the US, it's enteropathies such as IBD, and we've also done work in celiac disease. So we worked with a very, very, very large consortium across Pakistan, Zambia, Bangladesh, and the US. with funding from the Gates Foundation. I was a co-investigator in that project and access to a lot of that data, which again, for young investigators, I would say that's a great way to start your career. Look for a question within an existing data set that you can learn a lot of. That's where I got my initial NIH funding, my Career Development Award. And so, the project was focused on developing biomarkers for environmental enteropathy, which is very prevalent in low and middle income countries. It's characterized by small bowel structure and function alterations, leads to undernutrition and stunting. And really the biggest clinical link is that in patients with ED and stunting, you need often multiple booster doses of vaccines. And so the question is that it currently relies on a tissue-based diagnosis, which is expensive and resource intensive. So can we develop biomarkers for diagnosis that are non-invasive? You can see Fatma Zulkarnain, who is now a PEDS resident at UT Dallas, Yash, who is now working in industry and data science, and Philip Fernandez, who's actually just matched to start a PEDS GI fellowship at Stanford, and Shui Hong, who's a data scientist extraordinaire at Cincinnati Children. So our team led this, and I'll be focusing on the last three methods, the ones boxed in red. The first one is more digital histology, and I figured we already talked a little bit about that. We gathered data from 3 different countries, so Pakistan, Zambia, and the US. We got H&E biopsies from 52 ED patients in Pakistan and 25 controls in the US. And then we used this to develop a machine learning model to classify a batch as ED and control. So and once we classified that batch, so we were able to take that biopsy and reduce this into these 5 112 tissue features. So instead of saying a biopsy has 400 or 300 lymphocytes, and then have to correlate just that one feature, the entire biopsy was reduced into 512 ml features. And just to remind you, these are multidimensional. So the idea is you're able to capture the entire slide. And then what we were able to do is that we correlated this from bulk RNA-seq data that we already had from the tissue from the same patients. And so what we found here was that we correlated and were able to find these groups of, hang on, I'm going to go this way. We were able to find functional analyses of these genes in these groups of oxidoreductase activity, lyase activity, vitamin binding, transitional metal ion binding, transmembrane transport in organic anion transmembrane transport activity. The other thing we found was that when you correlated, so you see the circles, it says number of features. So and we focused on the bottom, the ones that are all the way to the right, which means these genes correlated with the most features on the histology. And the question was whether that has any specific significance. And so what we found was genes encoding UPB1, EPXH1, CYP453, highly correlated. And these 3 genes are related to immune homeostasis. They are inflammatory mediators. They're part of P450. So these are just sort of very interesting insights that, that would lead to further next round of research questions. So then we did this other very interesting thing called metabolic network modeling. And so what was done, what you can do is you can take gene count data and then put it in a metabolic model, which says for each given gene being up or down, how does that change the reactions? So flux across reactions. And so what we found that reactions involving fatty acid and glycerophospholipid metabolism had altered flux in both Zambia, so that was 30 patients from Zambia, and Pakistan's ED controls versus cohort. And then Shui Hong was able to do this really interesting lipidomics in Pakistan only. We showed increased LPC, ester-linked LPC, and decreased ester-linked LPC in the duodenal lipidome. The plasma levels of glycine conjugated bile acid was significantly increased. So overall, you can see that this has shown different ways of studying the genotype-phenotype relationship computationally. And then it kind of also might explain how the combination of inflammation, infection, and poor growth in children with ED works at a molecular level and potentially reveals targets for therapeutic interventions. So we have about 10-ish minutes left. I wanted to take a few slides about ethics. This is just a really important thing to think of because we've already seen issues related to AI ethics in our regular non-medical work. Ensuring patient safety, addressing algorithmic bias, monitoring and having transparency are really big areas to focus on. I put some names here on the slide. So Iran Denkva, she calls for more inclusivity in AI development, advocates for technologies that are diverse of all populations and promote accessibility. So for example, in that big model that's now a tool for capsule endoscopy, was there representation across ancestries? Was there representation across geographic areas? Because it may be that some areas where, say, you have changes in water, you may have more H. pylori, so you may see more difference in the gut from that perspective. The other thing to point out is continuous monitoring and evaluation is critical, and that's really for fostering trust amongst clinicians and patients. Floridi, who's pictured on the left, he explores the philosophical implications of AI and really argues for a comprehensive ethical framework considering human dignity and autonomy and justice. And then the two researchers on the right, Josh Cowell and Maria Rosaria, they offer insights into this. I was talking about logging into your phone using your face, which is really an idea of digital phenotyping. But they talk about the risks of digital phenotyping. So when you can use behavioral patterns to generate insights into a person's health, and then really overall who owns the data. And so with that, I'm going to end on this slide. This is just say a thank you to all my collaborators and members of my lab, both past at UVA and here at Duke. And then one final reminder of the power of histopathology and big data. This is a picture that was made by Peyton McBee, who is a PhD student, a previous member of my lab, and now works in the Air Force. This is Peyton's daughter from a few years ago in 3 different resolutions. And each of these images is a mosaic of 3 histopathology images. And so this serves as a reminder that the more sources of data we have with greater granularity, we can paint a clearer picture of our individual state of health and ensure we all get the right treatment at the right time, every time, which is sort of the dream in terms of logging into your phone or telling your patients what they need to get done. Thank you very much, and I'm happy to take questions.
Thank you so much for this great presentation. So until our attendees will start writing our questions, I have a couple. So you mentioned and you presented us the different areas where you can actually apply AI and machine learning. But I would like to ask you, what do you think is the most promising area in which you can actually apply in the pediatric care, of course?
So there was a slide I hadn't put in. I was thinking about it, but then I was like, it's in being able to pull data from the EHR. So there was the study, they've been doing adult studies a lot, but a couple of studies, you know how it's really hard to find and make cohorts. So unless you're actively developing a celiac cohort and you've kept it, now you want to study celiac disease, or you want to study patients with celiac disease and diabetes. That should be a really easy search in your electronic record. But again, I don't know how exactly it seems to be, at least in the US. And so I would say that's like the easiest, lowest hanging fruit, The other thing I found that I think would be very applicable, especially now that this is on the market, is just the video capsule endoscopy tool. The fact that you can reduce, time matters when you're a trainee. Yeah. If you can skim through, get these findings, and then it's much easier to skim through the video, because the goal is to find abnormalities. So I thought those two were very, very interesting. My personal area that I am very fascinated by is histology, because I think that it's just vastly underused. We just use it to say diagnosis, yes, no. There's a lot of information there that we've not really explored. And the last one I would say, I've just been fascinated by large language models. So both those ChatGPT examples, the one in GERD and the one for the GI questions, I just thought was very fascinating. I think it's taking over the world with the speed that you can't even recognize.
Yeah, it's I think AI is so complicated. It looks very easy, but in the end it's a bit complicated just to know when to apply it and how to correctly apply it also. And do you have any, I don't know, tips and tricks for clinicians and data scientists? How can they collaborate better? No, like clinicians and data scientists to just use better the AI for the pediatric care.
Yeah, I mean, I would think, the biggest thing that we can do as a society, both ASPIG and NASPIG and overall, is to collectively put together big data sets, right? Like if Mara, you say, I don't know what you're specific interested, but you say, you know what? I want to be the champion for pediatric capsule endoscopies and gathering that data in Europe, right? And we could have a, North American champion. That is a huge deal, right? That allows us to tailor whatever model that's out there and validate it in a pediatric population because we won't see this kinds of polyps and the types of hemangiomas, et cetera, that they would see in an adult population. I think getting data together is like that is huge value to a data scientist, right? Just giving them access to data that is, and then the second part is annotated. What's nice is while we don't have lesion level annotations in our clinical reports, we do have like a list of annotations, right? And so just pairing that and putting that up online or having it available through like a vetted resource, that would be just incredible. The other thing I would say is there's so many vendors out there. I would just say just try using whoever you want to use and then see, you know? I think that's the other really good way of seeing what attracts your attention.
Yeah, well, actually, one of our attendees asked us, where should we start learning from? Is there any platform you recommend? Any tips and tricks?
I would say I have enjoyed looking, like I read up stuff all the time across multiple. I've heard a lot about Coursera. Those are free courses. The ones that I showed in the first slide, the AAP's AI webinars, those looked really, really good. And so I would say, looking through those would be great also. Um, it's hard because it depends on what you want to learn off. If you want just a very global view, I would say just even things like Khan Academy would have those. The big ones I would recommend are Coursera, this AP one, and then Reddit is actually a really great
Yes.
forum. The deep learning Reddit, like people put in code there and they send edits,
Yeah.
you know,
Yeah.
that's a good.
Well. Yeah. Well, actually, my husband is always on the Reddit, and I always. Yeah.
Yeah, useful it is.
Yes. And talking about the future, what do you think is like the major breakthrough in the next 5 years in the pediatric AI?
Um,
So
wow.
the major breakthroughs, multiples.
I think so. What I can say is that let's look at the breakthroughs that have happened in the fields where there is more money and more data, right? The field that's leading all of that is cancer. So the big breakthroughs in cancer over the last 10, 15 years has been one, you have these big industry tools now for cancer histology, for cancer radiology, for like you name a modality, a diagnostic modality we use, and they have models for it, right? So then let's speak about gastroenterology. In adult gastroenterology, the biggest things that we have now are computer-aided sort of assist tools in clinical practice, like FDA approved. So you're doing a scope and something will beep and tell you you missed that lesion, or you're reading of it. So these kinds of things. So I think that the breakthrough in pediatrics ideally should be at least adopting some of these and then having people tailor them for peds. We won't know unless we try. And I think sometimes there can be more hesitance in peds. So we do need more people to do research, but we need people to do more to the bedside research. So just for example, this approved tool, right? You go, you do it on a large data set, and then you publish it, and then you approach the manufacturers, and then you say, we'd like a pediatric label for it, you know? I think that's the kind of things we have to do, just to say, um, just to kind of make the point that children are not little adults.
Yes, and it's complicated. For example, in Romania, it's a bit complicated just to try to even the idea of implementing AI is just not so well received in hospitals. So it's going to be a hard work for doctors to try to implement this.
Yeah, I mean, I think it's when someone hears the word AI, they worry. But if you say, here's a FDA approved tool that you can buy and just add on to your existing scope, then I think there's less worry about that because the marketing text for that tool will be able to answer a lot of their questions, right? And then, doing things as a trial is always useful to suggest. So, but I hear your point though.
And someone is asking if you recommend ChatGPT for like the clinical, daily clinical practice.
So ChatGPT has like several models. There's like ChatGPT 4, 4.0, etc. I use ChatGPT because I find it sometimes very interesting how it's phrasing an idea that I'm thinking of, But I use it, it's the caution. ChatGPT's training data has not been openly explained, right? There you can, they've said things like Wikipedia, but they've not said what all is trained in. Same thing like the DeepSeek algorithm that came out from China. They were a little bit more detailed. They said that they'd actually even used like large corpuses of Chinese literature in it. So all to say, yes, I do recommend ChatGPT to use it, but I don't recommend it blindly. I recommend like you look at it, you see the answer, and then you use your own brain.
Yes, yeah. Actually, like you said, I also use it for because I have some ideas and then I just put in some words and then he just
Train your
create.
ideas. Yeah,
Yes,
exactly.
yeah. Okay, so yes, I think that were all the questions. Thank you so much. It was super interesting, and I think it's just like this part in the pediatric care with AI and machine learning is at the very, very beginning.
Yeah.
So
You guys can do very easy things like what our fellows did with the ready-made tools that are already out there, just to kind of play around and see. I think the more you play around with them, the more you get. And I mean, I wouldn't push you unless you're interested, but I wouldn't push yourself to go do the coding. I would say, use the stuff that you already have access to, you can do easily. Like one of the things I've been wanting to do is we had a research study in which we were gathering tissue for genomics, et cetera. And we wanted to do a qualitative survey to understand patient perceptions. And so, typically these are semi-structured interviews and, it's like a yes, no, or like a line. And what we ended up doing was we added a prompt in which we just let them talk. And then we got permission to record that. And so we were able to do text analytics, right? And so again, that's just one way in which you can get a little bit more data out. So we use large language models to analyze that data. The other thing that we haven't done that I would love to do is that because we have recording, you can also analyze recording. And so one of the things I wanted to explore was, there's the people who were calling to ask about the surveys. One of our students was very, hello, good morning. And the other one was like really excited. And so, I'm very interested to see if the speed at which someone spoke led to more positive responses or not. Like those are just kind of fun questions that an AI algorithm can help you, analyze. And they're not, depending on how you do it, they're not particularly HIPAA protected, right? So if you, for example, wanted to use it as a training tool for residents or fellows, and you record trainees taking history, and then you have them do it fast, and then you do it like a slow way, and then so you kind of do. So do you understand what I mean? Like this
yes,
this is training stuff, and then you can use it on an existing tool out there.
yeah, that is nice. And just one last question. Someone asking, is there an AI tool that you would recommend for statistical calculations?
I mean, all of them do it now. So ChatGPT, Gemini.
Yeah, actually, I
See,
I try to do it with
like,
ChatGPT.
yeah. I actually really like DeepSeek. I don't know if DeepSeek's allowed anymore in the US, but when I initially used it, DeepSeek, because it actually gives all the back calculations and all the explanations, it doesn't just give the answer. But ChatGPT does that also now. Pediatric guidelines.
Yes, what are the pediatric guidelines other than up to date, which is kind of similar as World Health Organization AI?
Oh, I don't know about that. That's a great question. Let me look that up. To my knowledge, we don't have an up-to-date AI, WHO AI, but I'll look that up and see. I don't think. Yeah, so they have a WHO guidance on AI, and I shared the American Academy of Pediatrics AI guidelines. We have like review articles about Peds GI that we've done. We haven't put out a position statement. And again, I think that would be a fun statement to put out, like, so not just focused on endoscopy. Mara, you could help organize it.
Yes.
Position statement between Europe and North America.
I'm just going to write that down.
Or if there's a trainee who's interested.
Yeah. Yeah, there are so many things to work on.
I know. Yeah, if you guys can just put the link for the WHO AI for training purposes, I would love to look at that. I didn't know about that. Always learn something.
That's great. I hope they're going to put it here. And also, like, this webinar is going to be recorded, and if that's okay with you, we can post it then on YouTube, so we have all our webinars there, so for people to look again.
Of course.
Okay, kindly, is it possible to share the Prep Pediatric GI 2023 and 2024?
Like the questions themselves?
I don't know.
Mar, I'm not sure if I understood the question.
Yeah, me neither. Can you? Oh no. Oh. So regarding the also iOS. Okay, so it's an app on Play Store. So. Zakaria, can you please explain your question?
Questions?
Oh, thank you very much. Oh, I think I don't know. Sorry. Yeah. Okay, so I don't know regarding that question. He thanked us, so maybe we answered. Thank you so much for this great talk.
Do you have a couple minutes to chat, Mara, once this is done?
Sorry?
Do you have a few minutes to chat once?
Yes, of course. I can send you an invite too. Thank you so much. Thank you so much. Thank you everyone for attending this webinar, and hopefully we are going to see you again in our next webinar.
Bye.
Thank you so much.